Good evening, one and all. My name is Dr. C. Mahender. So I am working in assistant professor in Institute of Aeronautical Engineering College. Okay, so this is a coursework of nanochemistry. So continuation of the previous class. Okay, so last class we have seen the definition of nanochemistry and the synthesis rules of nanochemistry. Okay, so today we'll see some application parts and synthesis routes. So what is the objectives of today class is synthesis of nanomaterials, okay, and synthesis of nanomaterials, applications of nanomaterials, synthesis of nanomaterials, and we have discussed in last class synthesis of nanomaterials. We have bottom up approach and top up approach. So in nanomaterials, so applications is a very important. So first we'll see there's some few more applications. Last class also we have seen some applications, but here also we'll see some more applications of nanomaterials and the synthesis methods. Okay, synthesis methods, and we have no synthesis methods are a bottom up approach and top down approach. So bottom up approach means already the material has been synthesized, so we are bringing down to the nanoparticle size. And top down approach means we have when we are the synthesizing the nanomaterials, so at that time only we are converting that materials into nanomaterials. Okay, so we'll see, we have seen that nanotechnology, the study of design, production, characterization and application of nanomaterials. So this deals with the nanotechnology. And what is what we'll call as nanomaterials, we have seen in last class also definition. Finally we conclude the definition. Nanomaterials means the materials which have the size of 1 to 100 nanometers, or the materials which is having the size less than 100 nanometers. Okay, 100 nanometers will be regarded as nanomaterials. So we have also seen there are so many properties are changing from nanomaterials. Okay, so from we have also seen this. The word nano derived from a Greek prefix meaning dwarf or something very small. So something very small means 10 to the power of minus 9. So we know that the terminology 0.1 when size of the particle. So we are talking about the nanoparticle means talking about the particle size. So this is 0.1 means 10 to the power of minus 1, that we call as decimeter, or and 0.01 that is as centimeter, and 10 to the power of minus 2, and 0.001 that is a milli, that is 10 to the power of minus 3, and there is 0.000001 that is micro, that is 10 to the power of minus 6, and here our materials that is called 0.000000001, that is called that will be called as nano. The prefix will be nano, and 10 to the power of minus 9. The particle size will be 10 to the power of 9. So by seeing from this, so we can see the particle size will be very less when compared to the microorganisms. So these 10 to the power of minus 6 is a microorganisms, and this 10 to the power of minus 9 is very less size when compared to the 10 to the power of 6. So our human cell will be 10 to the power of minus 6 only. So our nanomaterials will be very less when compared to the human cell. So because of this size of the nanoparticles, it has a huge applications. So the main applications of the nanoparticles will be in medicines, and also it will be used in some surface coatings. Also it will be using in nano clusters also. So this mainly the main purpose of these nanomaterials will be used as a catalyst. Even though if we use the bulk material as a catalyst of 500 grams, if we use the nanoparticle, so 100 grams if we use the nano catalyst, that will be very enough, or it is equal to the 500 grams. And very important thing in the nanomaterials when compared to the bulk material and nanomaterial. What is a bulk material? Means the material which is at a normal size, and the nanoparticle means the particle will be less than the 10 to the power of minus 9. or equal to the nano size will be 1 to 100. So the properties of the nanomaterials is entirely different from the bulk material. So that's why this chemistry is called nanochemistry. So why it is called as nanochemistry means studying the properties of the material by bringing them into the very low size is called the nanochemistry. So we know that the properties of the gold is entirely different from the bulk gold, and the properties of the carbon. If you take carbon, will be the very good example. If you take carbon, so generally the carbon will act as a non-conductor or semiconductor, not non-conductor. It bulk material of the carbon, it will act as a semiconductor. But if you bring down the carbon into the nano form, it will act as a conductor. So that's why to study the making the material into nano size and what is the behavior of that particle is called nanochemistry. Okay. So we have one dimensional nanoparticles, that is a film, sheet, and surface coating. So last class also we have seen film, sheet, and surface coating. And what is a two dimensional? Two dimensional means if we measure in two dimension length or the breadth. So if we measure only one dimensional, that is called one dimensional nanoparticles or the one dimensional nanomaterials. If we measure the two sides length and breadth, that is called two-dimensional nanomaterials. And if you measure the three length, breadth, and height, if you measure the three, then it is called as a nanoparticles. Nanoparticles, 3D nanoparticles means three-dimensional nanoparticles, two-dimensional nanoparticles, and single-dimensional nanoparticles. So single or 1D nanoparticles will be observed in surface coating, in painting. So generally we'll use these nanoparticles or the nanomaterials in a surface coating. And two-dimensional will be nanotubes or the nanorods. And finally, the three-dimensional particles may be the nanoclusters or the nanomaterials individually. So we can see these are the nanoparticles. These are the nanoparticles and these are the nanoclusters. So these are the nanoclusters. Nanoclusters means combination of the nanomaterials together is called the clusters, nanoclusters. And single atom or the single particle of the nanoparticle is called this nanomaterial. Okay. We know that one dimensional, two dimensional, and three dimensional, depending upon the measurement, these nanoparticles are classified into one dimensional, two dimensional, and three dimensional. Okay. These are the some images. So these are some images of the nanomaterial, and these nanomaterials is called nanorods. These are the nanorods. So nanorods, we know that what is the difference between the nanorods and nanowires? Nanowires means that will have the halo in their material, and nanorods means all the material will be filled in the gaps. So this is not a cylindrical. This will looks like a solid. And the images which you are seeing is SEM images, scanning electron microscopy. Okay, these are the some images of nanowire. So these images are taken from the SEM characterization. SEM characterization means scanning electron microscopy. This is a scanning electron microscopy. These pictures are taken from the SEM images. These images are called SEM images. So we can see here nanowires. So these are the nanowires. Here is also nanowires, but different nanowires. This may be the zinc nanowires, carbon nanowires, and nickel nanowires. Depend upon the material, but I'm showing this is as a example how the nanowires will be looks like. So this is also nanorods. So nanorods, you can see the diameter will be filled in this one. This is a one type of a nanorods. Okay, now we'll see some characterization. So generally, nanomaterials have the characterization SEM, scanning electron microscopies. What is a scanning electron microscopy? These are the images of scanning electron microscopy. And TEM, transition electron microscopy. So what is the difference between the TEM and SEM? So scanning electron microscopy means this is not the light will not be penetrated into the materials. It is like a microscope only, but it will take the picture of the material. Scanning electron microscopy. TEM means transition electron microscopy. So in TEM, in TEM, So the light will be passed into the materials and it will give the picture. This is transmitted into the material and it will give the picture. So this is called transmission electron microscopy. That's why it is called as a transition electron microscopy. And this same means scanning electron microscopy. It is as it is that our microscope, but it will give the picture. It will give the picture, that is called scanning electron microscope. So in scanning tunneling microscope, so this is also one advanced feature of the SEM. And this is another one is AFM means atomic force microscopy. In this AFM, we can identify the composition of the nanomaterials. Composition of the nanomaterials synthesized. So these are the major characteristics will be done to the synthesized nanomaterials. So this will give the same TEM or STM will give the particle size of the nanometers. So we can see how this is this picture. So this picture is the TEM picture. So you can see this is the scale. Here it is written the scale means this is this round particle, this one which you are showing. So this is one particle and this is one particle and this is one particle. So this is the images of transition TEM, transition electron microscopy. So these are the bulk. You can see now here it is given some scale. This scale, okay. So from this one, transition electron microscopy. This is the this one is the images of transition transition electron microscopy. These are images, right? So now what is this one now? This is a same image. So this is a same image, okay. So and another important characterization of the nanometer is XRD. So XRD will gives XRD. So here XRD. So XRD we'll discuss in next class. XRD with X-ray diffraction. X-ray diffraction will give whether the synthesized is amorphous or crystalline. Amorphous or crystalline. So this XRD, most of the XRD will be done for the nanoparticles to confirm whether it will be crystalline or amorphous. So most of the nanoparticles will be always crystalline in size only. Always it will be crystalline. Okay, this is a basic characterization. XRD is a basic characterization to identify whether the particle will be or the powder or the nanopowder will be in amorphous or the crystalline. And from the XRD also from XRD we can conclude the particle size. We can also characterize the particle size and we can conclude by SEM and TEM followed by SEM and TEM, right? So we'll discuss some properties of the nanomaterials. So when going to the nano size, so when we are going to the nano size means when the size of any particle is reduced, when the size of the particle is reduced, so what are the properties are going to change. First one, falling the melting point. So the melting point of the particles will be decreases, and changing optical properties. So the optical properties of the bulk material also changes when it brings to the nano size. Then changing magnetic properties. So the magnetic properties of the material also will change when it bring down to the nano form. Increases the mechanical strength. The strength of the mechanical like temperature and the ductile property, malleable property of the materials also change when it is bring down to the nano size. And changing electrical properties also change. We have also seen one example how the electrical properties will change. So suppose if you take the carbon as a semiconductor, but if you bring down the carbon into the nano, it will be act as a conductor. So like that, all the particles changes its electrical properties also, or the conductivity of the properties. Some the changes in the particle will depend upon the particle to particle and the properties of the material. Increases the relative number of surface atoms. So definitely the surface area of the nanoparticles will be very more when compared to the bulk material, because the size of the particle is reduced to small. So the same particle will have the same surface area, but when we cut down into the pieces, the surface area definitely will increase. So this increase in surface area will enable the reaction, or these nanoparticles will be used in a catalyst, because in catalyst most of the catalyst will be based upon the surface area. So as the surface area increases, even if we use small amount of catalyst, that is enough. When we use the huge amount of bulk catalyst, okay, so these are the properties. So what are the properties? So melting point will change, optical properties will change, magnetic properties will change, mechanical strength will increase. So this is definitely the mechanical strength will increase. So all this, suppose we see melting point may decrease or increase, optical proper optical properties may changes, so electrical properties may changes, but mechanical strength definitely it will increases when we bring down to the small size. Okay, so we'll see some examples. Okay, we can see a melting point of the gold is 1064 degrees centigrade. This everybody knows, right? This is a bulk gold. Bulk gold. Okay. If we take the melting point of nano gold, so the melting point is drastically decreases from 1064 to 300 degrees centigrade. You see how much 700 degrees centigrade, almost the 700 degrees centigrade of the melting point is decreases when the same nano will be bring down to the same bulk gold will be bring down to the nano size. So we can see this graph by plotting particle diameter on x-axis and magnetic properties on melting point on y-axis. So we can see here almost our gold nanoparticle melting point is here, but when the particle size is 25 nanometers, almost, even though the 25 nanometers, even though if it is increases, but if you bring down, so you can see if you bring down the particle size to almost, it may be 1, it may be 1. When you bring down the particle size of the gold to the 1 nanometer, 1 nanometer. So what is happening? The melting point. So the melting point is around 300 degrees centigrade. So this is one of the important factor in nanoparticles. So when we bring down the nanoparticles to their very least level, the melting point will be reduced here, right? So we can see like that. We can see melting point. The melting point decreases drastically as a particle gets below 5 nanometers. So this is also one of the noticeable points. So this I have taken the reference source nanomaterials in chemistry. It is published in one journal. So you can see this is published in one nanomaterials journal. I'm taking for as example to explain how the melting point will be changes. So you can see here the particle size here, it is a 10. So when we bring down the particle size to around 1.5, so the melting point here, when you bring down the particle size to 2 nanometer, the melting point will be 500 degrees centigrade. So when the particle size is 10, when the particle size is 10, the almost it is 900, it is almost 900, but drastically you can see when the particle size is reduced to 4 nanometers, so the melting point is drastically decreases. So this is a, so we can see drastical changes when the particle size is 1 to 4 nanometers. You can see almost approximately all the same graph will be observed when the particle size is 10 to 4. But after when the nanoparticles is 3, so it is around 800. So now the nanoparticle is, if the nanoparticle is 3, it is 800. If it is a 2, it is around 650. Now it is a 1.5 nanometer size is 1.5, it is almost 500. So this graph clearly indicates that when the particle size is decreases, so the melting point also changes. But almost if the nanoparticle size is 9 to 5, it is almost same. But when it is bringing down to the 4, the drastical changes will be observed. So the study of these nanoparticles is called, purely it is called as nanoscience. Okay. So optical properties. So nanoparticles show different optical properties from that of a bulk material. So nano property, this optical properties also different from the nanoparticles when we compare with the bulk materials. So that will, the properties of the opticals will depend upon the properties of that material also. Okay. And one more important thing is conductivity of the bulk material, or this is called EG. So this EG is called forbidden gap or energy gap. So we can see from picture. So this red color, it is red, or this is pink, this is reddish pink, will be the color of this one is when the nanoparticle is 6 nanometers. The 6 nanometers, 6 nanometers, it shows reddish pink. And when we bring down to the 2 nanometers, it is drastically changes to the blue color. So when the particle size is reduced from 6 to the 2 nanometers, the color of the nanoparticles will be changes to blue color. So this indicates when the color of the nanoparticle will changes, the conductivity of the nanoparticle, the conductivity of the particle also changes. So we can see here the forbidden gap. So this one is called forbidden gap or the energy gap, or it is called the band gap. So band gap between the particle. Okay. So band gap between the particles. So when it is a 6 nanomaterials, so we can see this is the band gap between the conduction bond and valency bond. What is a conduction band and valency band? So we know that solid state theory. So conductors are classified, materials are classified into conductors, non-conductors, and semiconductors. So conductors means almost the band gap between the conduction band and valency band is almost overlapped. Whereas in semiconductor, there is a gap between the conduction band and valency band. Okay, this conduction band and valency band indicates the conductivity of the material. In semiconductor, the valency band, in semiconductor band gap, this is called forbidden gap or the band gap. So this plays a prominent role how much conductivity that material will shows. So we can see the huge band gap will be there here. So when the particle is bringing down to the 2 nanomaterial, so there is a huge gap between the valency band and conduction band. Valency band and conduction band means here the energy gap is more. When the energy gap is more, that will be considered as very good semiconductor. So the properties of the semiconductor will be depends upon the energy band gap. As the band gap is more, that will be considered as a very good semiconductor. But the same material, if we bring down to the nano size, or if you are reducing the size of the nanometer, the band gap can be increased. So if we increase the band gap, the absorption capacity of the material will increases. So this will enhance the conducting properties of the material. So this is also one of the important factor in the nanomaterials. So in titanium dioxide, so mainly titanium dioxide, so generally titanium dioxide will absorb the UV IR rays, but when it is bringing down to the nano phase, so it will be absorbing the UV light. So that is because of the band gap only. So we can conclude from this one, as the band gap, as a nanoparticle size decreases, the energy band gap increases. As the energy band gap increases, the conductivity of the material increases, and the semiconducting properties of that material will increases. So from this we can conclude, if any material is bringing down to the nano size, can change its conductivity. And this is the how the changes will be occurs. Suppose you can see here, we'll take the graph by plotting on x-axis diameter and y-axis and y-axis we will take the band gap energy. Diameter is nothing but the particle size. So as a nanoparticle size is increasing, suppose if the nanoparticle size is 55, so the band gap energy is only 1.7. Here we can see the particle size is the diameter is 50, around 51 or 52. So the band gap energy is almost 1.5. So as the same the nanoparticle size is diameter. So diameter or the nanoparticle size. Nanoparticle size means it will be considered, diameter means it will be 2 into its particle size. So now if it is 1.5, you can see here the particle size is 1.5, the band gap is 2. Now the same particle, if the 50 nanometers will have the, here will I write, so 50 nanometers, it will have the band gap is 1.7 electron volts, and the same nanoparticle if we bring down to the, how much, if it is 50 nanometers, the increasing, what is the band gap, it is, what is the band gap, it is almost this one will take, okay. So this one it is around 2.3. So 2.3. So the band gap, here you can see the band gap at a bulk material is 1.7. As the same the material, if we bring down to the nano size, the band gap energy is increases to 2.3 electron. The band gap will be measured in electrovolts. So from this we can conclude band gap energy also increases. As in any semiconductor, if the band gap energy plays a prominent role, as a band gap energy is more, that semiconductor will be considered as very good semiconductor. Okay, so here from the particle size also we can also vary the band gap. So the study of all these properties is called the nanochemistry. Okay, we'll see another properties. So now we will see another important properties of the nanoparticles. So cadmium sulfide, if you take cadmium sulfide in bulk appears as a red, but 6 nanometers cadmium is orange, 4 nanometers it shows yellow, and 2 nanometers it appears as a white. So you can see if we take the one of the example of cadmium. So cadmium when it is in 6 nanometers, it shows the red color. So this one 6 shows it is a red color. So when it bring to the 4 nanometers, it shows yellows, and when it bring to the 2, it shows white. So the nano color of the particle also will changes when the nano size of the material is changes. So we can see how the material's color is. This color indicates the energy of that material. So energy, if it is red, means that will be considered as very high energy when compared to the white. So the energy of these particles is also changes when it is bringing down to the low size of the nanomaterials. Okay, this is also one of the properties that explains how the properties of the particle will changes when the size of the particle is decreases. And another important thing is optical properties. For example, zinc oxide. Will not be used as a sunscreen. Zinc oxide will not be used as a sunscreen application of sunscreen, because at bulk zinc oxide that will scatter the light. Whereas if you take zinc oxide, if you take the nano zinc oxide, so that will not scatter the light, that will not allow the light. So because of that purpose, this zinc oxide will be used in a sunscreen lotions, so that it will protect from the UV light. Because if the nano zinc, if you take this nano zinc, the nano zinc will have the capacity of scattering light, whereas bulk zinc. Whereas if you take the nano zinc, that will not allow the light to scatter inside, so that it will be used as a scatter. We know that why the sunscreens will be used. Sunscreens will be used so that it will be protected from the UV light. So that's why zinc oxide is one of the material which will be used in sunscreens. We can see This is we have seen. So this is one of the TEM images of the zinc oxide particles. Okay, so you can see because of these properties, zinc oxide will be, because of the nano properties, zinc oxide will be used as sunscreen. Whereas if the bulk zinc oxide will not be used as a sunscreen, because there is a no use when we use the bulk zinc oxide. If we use a nano zinc oxide only, that will protect from the sunlight. So we can see here, we will see what is the properties. Bulk zinc particles block the UV light. Okay, scatter visible light, appears white. Okay, this is the properties of bulk material. If you see the nanoparticles, block UV light, so this is same, there is no change. But here don't scatter visible light. Here this is a very important property. This makes the difference of bulk and nanomaterial. So this means don't scatter the visible light. This don't scatter the visible light means that can be used as a sunscreen. So that's why only nano zinc oxide will be used as a sunscreen, whereas normal zinc oxide will not be used as a sunscreen because it will not protect from the UV rays. Like that, we'll see magnetic properties. There are also some magnetic properties also will change. So we'll see by taking a graph, particle size on x-axis and magnetism and magnetization on y-axis. So we'll see, as the particle size is 80 nanometers, the magnetism of this one is only 0.8. So you can see, we'll see one example. This is 80. When the particle size is 80 nanometers, so this is the magnetic momentum is only 0.8, means 80 nanometers, it is 0.8. Okay, so but same the particle size is, suppose this is 10, the same particle size if you bring to the 10, it is 9. So same if it is 10 nanometers, it will be bring to the 0.95. So we can see how much change will be there. So when the particle size is 80 to 10, so when the particle size is reduced, the magnetic properties is drastically changes. So still here, when the particle size is 20, there is no change or almost the same change. But when the particle size is bring down to the 1 nanometer, so the magnetic properties will be changes. So that's why this nanochemistry will be very important to study the characterization of the particle. Based on the size of the particle, the properties will be studied. That the study of properties based upon the particle size is called the nanochemistry. So now, mechanical properties. So what are the nanomaterials are having high nanomaterials are having high flexibility. Nanomaterials are having high flexibility. What is this high flexibility? Suppose it shows one property at one particular size, and another particle size it shows another properties. So that's why it has a very flexible, and it shows another property in bulk material. So based upon the size of the particle, the properties of this one change, and at what particle size what properties are changing. To study and to analyze all this is called nanochemistry. Okay, flexibility is measured by Young's modulus. Okay, flexibility is measured by Young's modulus. The Young's modulus is 10 times greater than that of a steel. Okay, their Young's modulus is 10 times greater than that of a steel. Greater than that of steel means when we take the bulk material, if you consider the same steel into the nanomaterial, the Young's modulus of that material will be 10 times greater than that of the material. Okay, due to less defects of nanomaterials, the mechanical strength is improved. So there is in the nanomaterial, the defects in the material are also very less, because in nanomaterial, the nanomaterials will be almost in atomic size. So in atomic level, if you go for the atomic level, the purity of that material will increases, because all the atoms will, we know that which one is a more pure means the atom is a very pure, right? So atoms are very pure. So this nanochemistry or the nanotechnology will be bring down the material into the atomic level, so that the more purity when compared to the bulk material. That's why, due to less defects in nanomaterial, because of this, because of the atomic size. The atomic size, the impurity levels are very less, or almost it is a pure. So that's why the defects also will be very less, or there are no defects will be there in nanomaterials. Okay, so this one, so this will be considered as atomic level. So these defects will be very less. And okay, increased internal perfection. This one is increased internal perfection, and this one is surface one. Okay, electrical property. If we are going for the electrical property, conductivity decreases with reduced dimension. Conductivity decreases with reduced dimension due to increased scattering and decreases delocalization. Okay, increased surface scattering and decreased delocalization. So when we bring down to the size of the particle, the delocalization also decreases. So this delocalization decreases means the conductivity automatically. The conductivity is because of the localization of the electron, or the delocalization of the particle, or the delocalization of the electron moving in the surface. So when we bring down the particle to the very low size, so the delocalization will decrease. This delocalization automatically decrease the electrical conductivity. And when we bring down the particle to the very low size, that increases the surface. The same particle, if we cut down into the number of pieces, the number of pieces will increase the particle size. So we'll see in the next example. Okay, so this chemical properties. So what are the chemical properties? Water resistance, chemical resistance, and corrosion resistance are improved. Okay, so increased total surface area. Anyway, the total surface area of the nanometal will increase when compared to the bulk material. Increases number of atoms on the surface. So this increases the number of atoms on the surface. The same surface, if we reduce the size, the number of atoms will increases. As the number of atoms increases, the active sites on the molecule increases. As the active sites increases, the rate of reaction also increases. Okay, increased catalytic activity. As the number of active sites increases, the catalytic activity increases. So the catalytic activity will be based upon the how much activity will be there. So we can see one of the example. You can see this is a bulk nickel. So 1, 2, 3, 4, 9 atoms. So this is consider this one number. So this number is one active site. This number is one active site. These numbers are 12 active sites. 12 reactive sites, or we can also call as a active sites. So we can see if we take the nickel, normal bulk nickel, means the nickel which is at a normal size. So there are 12 active sites for this one. The same nickel, if we bring down after size reduction. So after, if we are cutting, side reduction means, so we are bringing down this, we are cutting this particle. This is a particle, so we are bringing down this particle into 2, and we can also reduce the 3. So like that. So we can bring down the particle size into reduce. So this one particle, suppose if you take this one particle, if you reduce into the 4 particles, means one active site will be increases the 4 active sites. Now, do you understand? Suppose this is one, if you consider this as a one of the bulk nickel. This bulk nickel, if you bring down, and this bulk nickel will be cut into 4 pieces. So what will happen? Now the 4 active sites will be increases. Now it consider the 4 active sites will be increases. So now we will calculate 9 into 4. 9 into 4 is 36 reactive sites. Now it will have the 36 reactive sites, whereas for this bulk nickel only 12 reactive sites. So the catalytical property of any material will depends upon the active sites. Now it will have 36 reactive sites, whereas it will have 12 reactive sites. Now it is increased to 3 times. It is increased to 3 times. The catalytic property of the nickel will increases to 3 times when it reduces to nanomaterial. This clearly indicates that when you decrease the size of the particle, the catalytical property of this nickel will increases to 3 times than the bulk material. Suppose if we are adding in any reaction 1 kg of nickel we are adding. So if we want to take the nickel in a nano form, 1 kg is enough. Instead of 3 kgs, if we add 1 kg, that is enough. Okay, so that is the that indicates the nanoparticle importance, right? So next class, and this is also one of the, if we take one cube, if we take one cube, this how many sides, what is the surface area of this cube is 96 centimeters square. 4 into 4 means, suppose if you consider this is a length, breadth, height is 4, length, breadth is a 4, and it has a 4 faces. So if we calculate the surface area of this cube, 96 centimeters, the same cube, if we cut down into the same cube, if we cut down into 8 pieces, now what is the surface area? 2 into 2 into 6 faces, 24 centimeters square. Each cube will have now 24 centimeters square. This 24 centimeters square, again this cube is divided into 8 parts. So now we can see the surface area of the bulk cube is 96 centimeter. The surface area of this cube is 192 centimeter. You can see how much surface area is increases. So this surface area plays a prominent role in catalytical reactions. So that's why you can see the same cube is cutted into 8 pieces, right? The same is cutted into 8 pieces, and if you measure the surface area of that cube, so it is a 192 centimeters square, and this is 96 centimeters. So you can see how much surface area is increases. So mainly, surface area plays a prominent role in catalytical reaction. Okay, so next class we'll see synthesis of nanomaterials, a bottom up approach and a top down, so how it will be synthesized. Okay, so we'll see the next class, this what is the chemical vapor deposition, sol gel process, chemical reduction, and what is the mechanism of this one. Okay, so these are the some references. So these are the some references. So the references are Essentials of Nanochemistry by N. Kumar, and Introduction to Nanoscience and Nanomaterials by Dinesh Agarwal. So this we can available in the online. This is this is DOI. And another textbook is An Introduction to Nanomaterials and Nanoscience by Asim K Das, CBS, and publications, CBS Publications and Distributors Private Limited. So I have collected this material from the references. Okay, so thank you.
Like, share and subscribe. Hit the bell icon for more updates.